This is called a matched pairs t-test in all its steps. Okay, this is problem 12.9. Let's read it and see what it says. It says the degree of controls, the design of controls and instruments affects how easily people can use them. A student project investigated this effect by asking 25 right-handed students to turn a knob with their right hands that moved an indicator by a screw action. There were two identical instruments, one with a right-hand thread, a knob that turns clockwise, and the other with a left-hand thread, a knob that turns counterclockwise. The following table gives times and seconds each subject took to move the indicator a total fixed distance. So if we look at the chart here, the first person, when they had a right thread, their total time to twist it was 113. And when they had a left thread, their total time to twist it was 137. So you can see it took the person a longer time to spin the left thread than the right thread. The second subject had times of 105 and 105. So that person, it doesn't seem to matter what type of thread it was. The third person has 130 and 133. So that person was actually a little bit slower in turning, a little bit slower in turning the left thread. Okay, then one more down, and then you have 101 and 108. Okay, so you can tell in this case what we'd be interested in is the difference. We would care about how much faster was the same person spinning the right-hand thread versus the left-hand thread. Okay, and we might suspect that this column here would have lower times, and the reason we would expect that is because these people are all right-handed. So maybe right-handed people are going to turn right-threaded screws more quickly than left-threaded screws. So we would be interested in the difference here. We would subtract all these numbers. Here's a difference of 0. Here's a difference of, now we need to decide here how we're going to do this. Do we want to do left minus right or right minus left? So we're going to let mu equal the right thread time minus the left thread time. I should say the mean of the right thread times minus the left thread times. Okay, and then there'd be a set of differences for all of these. So if I did right minus left in the last case here, I had -7. Right minus left here, -3. Right minus left here, before I say the wrong thing, so -24. All right, so this looks good so far. I'm seeing a lot of negative differences, sort of confirming what I'm suspecting, that the people would be faster at spinning a right-hand thread than a left-hand thread. A problem like this screams out match pairs, because some people are going to be better at twisting screws than others. Like for me, for example, I have lots of experience with using screwdrivers, okay, and fixing things. So my times would generally be lower no matter what the thread was. Okay? Okay? So let's get our calculator out and put some of this information in. So we're going to go to Stat Edit, and our plan is going to be that we're going to go to List 1, and we're going to put all the right thread times, and then in List 2, we'll put all the left thread times, and then in List 3, we're going to subtract. So I'll start this briefly, and then I'll spare you this, but it's going to be 113 here, okay? And then next to that number is going to be 137 for the left thread. And then we'll just continue in that fashion until we have all our data in there. So we have all our data in here, and you can see that for each pair of information, right? For example, this means the person took 78 seconds to spin it to the right-hand thread while taking 76 seconds to spin the left-hand thread. Okay? But you can see generally the numbers in List 2 are bigger than the numbers in List 1. That's sort of telling us that it took people longer, except for that one exception, the 122 and the 84. But generally, it took people longer to spin the left-hand thread than the right-hand thread. So there's all the information. You can see it all. So we're going to go here to the top of List 3, and we're going to be consistent with how we define things. We said mu is going to be the right-hand thread minus the left-hand thread. Or in our case, it's going to be List 1 minus List 2. And we would expect quite a few negative numbers here, indicating that it took them They were faster with the right-hand thread than the left-hand thread. Okay. Let's state our hypotheses for a minute. So our hypotheses are as follows: that there is no difference between the left and right-hand thread, that people spin these things the same rate. That would mean that mu is 0. And an alternative hypothesis, since we suspect that the right-hand time will be less than the left-hand time, we would expect mu to be less than 0. We'd expect a negative average, meaning that there were faster times for the right-hand thread. All right, so you state your hypotheses. The next thing you have to go and do is check your assumptions. First of all, if there was an SRS, yep, that was true. Population of all people was greater than 10 times our sample size, which in this case I believe was 25, so 250. That's called the independence test. Okay, and while we're here, we might as well make a note. Our S of x bar is going to be S of x over the square root of n. Remember, this is called the standard error. You need to know that word. You use the standard error when you don't know sigma, the standard deviation of the population. And in this problem, we did not know that. All right. The last check is for normality. And in the case of a t-test, we need to remember the information we talked about what size n is and what you need to do. So in our case, n was 25. That's between 15 and 30. We need to check a box and whisker plot, and we need to check a normal probability plot and hope that the plots are reasonably symmetric and the normal probability plot is reasonably linear. Ready? Let's take a look at this. So we're going to check two graphs. We're going to go second stat plot. And while we're at it, I already have this set to the normal probability plot, so I'm going to do that. And my data is in list 3, the differences. So I'm going to go zoom 9 and check that normal probability plot. Oop, something is a little strange there. I must have entered a data point wrong. I better go back to stat edit for a minute. Let's take a look at this. Fixed, found it. All right, so now this thing here would be 107 minus 87. Okay, so that's 20. So that's going to be a little bit more reasonable. I'll press zoom 9 now, and I get a pretty nice graph. There it is. If you look at it, you can see it's fairly linear. That's good. So the MPP is linear. That implies that our data come from a normal distribution. So that's important. Now, we should also check for skewness and outliers, and that's probably not going to happen, but let's just make sure. All right, so we go back to stat plot. It's going to be the same list, just a different type of graph. So we go to the fourth type, which is called a modified box plot. Okay, we're still using XList of L3. We do zoom 9 and look at the graph. And that, too, this is pretty good because we don't have any strong skewness, right? So no outliers. And really, I would just say small skewness. So this implies that the T procedures are safe to use. That's what you want. You want to make sure that these things are safe to use. So your assumptions are done. We're ready to start finding a t-score. Okay? So a t-score looks like this. It's x bar minus mu over the standard error, S of x over rad n. Okay? Now, we need to get x bar, and we need to get S of x. But you're going to get that by doing the one variable statistics. Oops, put the number 1 there. One var stats. And then we'll have all information. So here we go. So you go to stat, go over to calculate, one variable stats. Make sure you select list 3. If your calculator displays a frequency list, don't put anything in it. Leave that blank. Okay, we hit enter. And we have an x bar of negative 13.32. And we have an S of x of 22.9. So x bar equals negative 13.32. S of x equals 22.9. Now, I'm not surprised by this negative number for x bar. I was expecting that. I was expecting, generally, the right-hand threads to be lower times, right? So let's fill things in and see what we get. T equals negative 13.32 minus 0 over 22.9 over the square root of 25 in our case. Okay? All right, so this is about negative 2.9. So that's a lot of standard deviations away. Now we need to figure out what that means. Well, in this problem, we can draw a picture. We can put something that looks like a normal distribution, but really it's a t-distribution. And we can put mu equals 0 in the middle. And we know we're pretty far away. We're t equals negative 2.9 standard deviations. The question is just simply, what's that area? Okay? Well, let's not forget, n was 25 in this problem. That implies that degrees of freedom is equal to 24. So what we're going to do is, we're going to look in our t-table, and we're going to find 24 degrees of freedom, and look across in this row for a t-score that's close to it. Okay? So now, if I look across in 24, I'm noticing the following. I have to go all the way. I find two numbers. I find the number that says 2.797, and then next to it, 3.091. Okay, and if I look at the top of those columns, one is 0.005 and one is 0.001. So what you'll notice is, when I look in this column or this row, I never find t equals negative 2.9 exactly. It's not in there, right? But I found two numbers that it's between. It's between this number and this number, which correspond to these tail areas. Okay, I made a small mistake here. This is 0.0025, not that. Okay, so what you'll notice is that means that this area here, our p-value, is between 0.005 and 0.0025. Right? That's what we know from our table. So is our result significant or not? Yeah, our result is significant, and we can reject HO in favor of HA. We can say that the time that it takes for someone to spin the right-hand thread is indeed quicker than the time it takes for someone to spin the left-hand thread. So you could actually do this t-test in the calculator. So let me show you how to do that. Go back to the calculator. If you go to Stat and you go over to Tests, the second thing on the list is the t-test. You'll remember in a few videos ago, we went down and we used the z interval and then the t interval. But today, what we just did is considered a one-sample t-test. The calculator just calls it a t-test. And when we hit Enter, what you'll notice is, if you have done one variable stats already on list 3, it will have that information in here for you. Okay? We suspected that the alternative hypothesis was that the mu would be less than 0. Everything's there for you. We go to calculate, and you're going to notice some familiar things. Oh, hold on a second. Stat test. I must have hit Enter too many times. Let's do this again. We'll go to calculate. Go down here. All the things are in there. One more. So you'll notice, if we look at this output, there's some pretty familiar things. So here's what you'll notice. First off, there's your t-score right there. Okay. Here's the p-value. And my claim is we shouldn't be surprised by that, because when we looked at the t-chart, we noticed that our p-value was less than 0.005, but greater than 0.0025. And the p-value the calculator is telling us is 0.00389. All right, there's the x bar we had, there's our s of x, there's n. So the advantage of using the t-test in the calculator is it reports to you the exact p-value. And once you have the exact p-value, you can compare it to alpha. Now, usually, we use alpha equals 0.05. Well, clearly, that's less than, our p-value is less than that. Our p-value would even be less than another common alpha of 0.01, 0.01, that is. All right? So this just confirms that we would reject HO in favor of HA, and that the true mean difference from left-hand thread times to right-hand thread times is actually less than 0, and thereby confirming that people spin the screwdriver more quickly with the right hand rather than the left hand.